In the previous video, we considered the rectangular form of a complex number and the Argand diagram. To see the video, just click on the link at the top right corner of your screen. So in this video, we're going to be considering the polar form of a complex number. We know that a complex number z in the rectangular form is z equals x plus iy, where x is the real part and y is the imaginary part. I can plot this complex number on the Argand diagram. Already I know that the y-axis is the imaginary axis and the x-axis is the real axis. Thus, I've got the real part here, x, and all of the points on the real axis are arbitrary values of x. So I could just pick an arbitrary point here, x, and do the same for y here. The points here is going to be the coordinates of x and y. So the complex number is just going to be this line from the origin right to the point of intersection of x and y. So this is the complex number. And of course, I would see that this complex number is a straight line. So I can take a measure of its length. And we know that if z is a complex number, introducing it between two straight lines would represent the length of the complex number. And also, since the distance from the origin to this point y is a vertical line, I can just replicate it here, right here, and do the same for the x-axis. So what this tells us is that we've got a right triangle for ourselves here. So we would see that the triangle OPQ is a right triangle. Of course, the right angle is going to be here, right here. Now, we would also see that the line OP, which is the length of the complex number, also makes an angle with the x-axis. I'm going to call that angle theta. Since this is a right triangle, of course, I can apply my Pythagorean theorem because already I have OP, which is the hypotenuse. PQ is going to be the opposite of angle theta. And of course, I know the length of PQ. That's the length of the imaginary parts. That's y. And I also know the length of OQ. That's the real part. That's x. Thus, if I apply one of the trigonometrical ratios of tan, because what I need is the y and the x, which is the opposite and the adjacent. So we would see that tan theta, which of course is the ratio of the opposite to the adjacent, this is y over x, which implies that theta is going to be equal to the inverse tan of y over x. So if a complex number is represented by z equals x plus iy, the angle is going to make with the x-axis is the inverse tan of y over x. This angle here is called the argument of a complex number. Similarly, since we are dealing with a right triangle here, I can also apply the Pythagorean theorem. So the Pythagorean theorem states that the square of the hypotenuse is equal to the sum of the squares of the opposite and the adjacent sides. Thus, we would see that the hypotenuse here is the length of the complex number z. And of course, I can just represent it with r, the radius. So this is r squared equals, now the opposites, that's y squared, and the adjacent, that's x squared. By convention, I always like to have the x before the y. So r squared equals x squared plus y squared. If we take the square root of both sides, r is going to be equal to the square root of x squared plus y squared. This is called the modulus of the complex number. Of course, earlier I said that the length of z is OP, of course, that's OP, which I've represented with r. This is called the modulus of the complex number z. And we know from one of our previous videos that modulus is just a measure of length. So these are the two parameters we are going to be needing in dealing with complex numbers in polar form. What this diagram tells us is that a complex number can be represented by two parameters, the radius and the argument. By radius, I mean the modulus of the complex number and the argument of the complex number. So how do we convert a complex number from the rectangular form x plus iy to another form involving just theta and the modulus of the complex number? Now we are going to go back to our diagram and apply the remaining two trigonometrical ratios. We already applied tan. Let's see what happens if we apply the sine and the cosine. Let's begin with the sine. From the diagram, we would see that the sine of the arguments, which is theta, is equal to the ratio of the opposite to the hypotenuse. The opposite here is y. The hypotenuse is the modulus of the complex number, that's r. And this tells us that y is equal to r sine theta. Similarly, cos theta is equal to, of course, cos is the ratio of the adjacent to the hypotenuse, that's x over hypotenuse, that's the modulus. So we can see that x is equal to r cos theta. And already we know that the complex number z in rectangular form is x plus iy, and x is r cos theta, so this is r cos theta, plus y is r sine theta. So this becomes I r sine theta. And since r is common, I'm just going to factor that out. So I would have r brackets cos theta plus I sine theta. What we have here theta is the polar form representation of the complex number z equals x plus I y. So this is the rectangular form and this is the polar form. And the polar form here, since we've got two parameters, r and theta, is also written as r, this symbol that looks like a less than, then the angle theta. So the polar form can be written in either of these two ways. Thank you for watching this video. If you find it useful, kindly like it by giving it a thumbs up, share to your friends and colleagues on social media, drop a comment, and click on the subscribed icon. To get notification if I upload new videos, just check the dark bell button under the subscribed icon. Thank you for watching once again, and see you in the next video.